Good evening, everyone, and welcome to our April Research Tuesdays Forum, Engineering Champions. I'd like to first acknowledge the Kaurna people, the original custodians of the Adelaide Plains and the land on which the campuses of the University of Adelaide are built. I'd also acknowledge elders past and present. My name is Anton Middleberg and I'm the Executive Dean of the University's Faculty of Engineering, Computer and Mathematical Sciences. As many of you will know, the Commonwealth Games are currently underway on the Gold Coast in Queensland. There's a lot to love about the Games. It brings together the countries of the Commonwealth. It lets us celebrate success with those who win and those who try to win, and it lets us watch the fastest, strongest and bravest compete in one of the world's premier competitions. Here at the University of Adelaide, we also see the Commonwealth Games as an ideal opportunity to reflect on the work that we do in sport engineering and to share with the community some of the work that we do in sports engineering. Our university's contributed to sports science and technology for decades. Richard was just telling me he joined the university staff in 1995 and has pioneered some of the sports engineering work in the university since then. We'll hear from him shortly. These days we also have a course dedicated to sports engineering, and our academic and students are making some significant contributions to the world of elite sport. In fact, within the university's elite sport program, one of our fourth-year sport engineering students is swimming. Tonight you'll hear from three of our top sports engineers and how they're giving athletes at the Games a real edge. So I sat there a moment ago talking to Richard about what that means, giving the athletes a real edge, and I pointed at this bike. And he said, without the pedals, it's really aerodynamic. And I sort of reflected on that, and I thought that's where actually the intersection between academic and reality work really comes to the fore. And Richard does that very well because he recovered quickly and said, of course, the athletes bring their own pedals. So I was a little more comfortable at that point, and I was also comfortable that the research and the impact of that research are meeting in an engaged fashion. Anyway, I've built you up enough there, Richard. Richard is the Associate Professor in Mechanical Engineering, who's our Senior Researcher in the Sports Engineering area. Amy Lewis is a final year PhD student in Sports Engineering, will also speak today. And Sean Fitzgerald is our second year Sports Engineering PhD student, who will also present. They'll each present on their work, and then at the end come back to answer some questions from the floor. So I encourage you to think up more of those curly ones about why that bike should work, or other such things. So without further ado, it's my pleasure to introduce Professor Richard Kelso, who will lead the following presentations and discussion. He has been very involved, particularly in helmet design. He developed the Scott Sports Cadence Plus cycling helmet, which is considered one of the world's fastest. And last year, 2017, was recognised in Engineer Australia's most innovative engineers list. Richard, welcome.
Hi everyone, I just want to check that you can all hear me. Good, thank you. Yep, that's great. So, what's there to gain from all the work that we do? Well, a group of researchers in 2008 suggested that physiologically humans were reaching peak performance, that really there wasn't much to improve. It was really only going to be physiological outliers that would really make any improvements. I think they must have had a lot of flack from their colleagues about that, because there are plenty of sports where that certainly isn't true. So in 2015 they added to those comments and also said that technological improvements could actually help to improve records. Oops. So what I've prepared here is a slide with world record progression. Now, what this is it's the world record for 4 different events, and I've divided that world record, which is shown across there for each year, by the current world record. So what we see here for the men's 1500 metres running race, that they've improved by around about, say, 28% since the late 1880s. And so it goes for all the others. In 400 metres freestyle, they've improved by approximately 55%, let's say, 53%. So all of these are 4-minute events, or very close to that. So physiologically, they're around about the same. People their bodies are behaving in roughly the same sort of way. So they're really quite a good comparison. So here we see the 1500 metres running race, and that's a natural activity, and we're all born with the ability to run. And we see it's a fairly flat progression. There are a few dips and bumps and flat bits due to world wars and things like stadium materials being, or stadium running surfaces improving and shoes improving, but it's a fairly flat progression. In the 400 metres freestyle, we see a much steeper rate of decline in the records, and we can attribute that to improvements in stroke technique. It's not necessarily a natural technique for us to swim, and so improvements in stroke technique have made a great deal of difference, also swimsuits and a number of other factors, and so we see a much steeper decline. Now there are two cycling events here. One's the men's individual pursuit with the gold, appropriately coloured, and then the team pursuit with the blue crosses, and they both start a bit later, and they show an even steeper decline. The next slide is really looking at the 1960s and up to the present for all of these cases. Now the men's 1500 metres hasn't improved since 1998, so that's possibly suggestive that we have reached something fairly close to a physiological optimum, or we're not going to improve very much from now on. Swimming, we see that same progression. Now that's Ian Thorpe there, who obviously made a significant contribution, and this last one was a swimmer who was wearing essentially a plastic swimsuit. And in the early 2000s, there were most swimmers were using plastic swimsuits, or swimsuits that eventually culminated in essentially polyethylene suits, which reduced drag quite a lot, and so there were huge, there are records that may never be broken because of that, particularly in the sprint events. So that's one example where technological innovation can make a big difference. So in the cycling races, we see something similar. The blue crosses are the team pursuit, the team race, with a number of riders running together in a bunch, and the gold triangles are the individual pursuit, an individual rider in a very similar position. And what we see here is a significant jump in 1995 or 6, where a rider called Chris Boardman use a new position called the Superman position to drastically reduce his drag, and we see this huge drop. His record wasn't broken until 2011. It was broken by Jack Bobridge. And so here's another example of a technological innovation. In this case, it's a position innovation that made a huge huge improvement. Now, all the intermediate data, there are a whole lot of performances, other performances using the more standard position that run through here and kind of fill in this data, but they're not shown here, that they weren't world records. So here's another example of world record progression in 100-metre sprints for the standard 100-metre event, and then the T44, men's T44 para athletes, here's their progression of records. Now T44 is for athletes with one leg amputated below the knee, or some other occurrence that leads to them essentially being missing one of their feet. And so they use some kind of artificial foot. Now, up until around about 1984, essentially people used wooden legs. And so the world records were up here. In 1984, an American engineer developed a leg with a spring and a foot with a heel called the flex foot, and that produced that record. Then they deleted the heel and produced something like Oscar Pistorius used, and suddenly the records dropped, and they dropped and they dropped. Huge improvement. In fact, Oscar Pistorius, who is credited with a lot of these, as bringing this innovation to the world, in fact, he went up a class to this class, to T44, and set that record. But he was just one of many athletes along the way. What we see here is the effect of technological innovations, particularly in a sport where there are disabilities that need to be taken into account. So, what does this tell us? Well, we're approaching physiological limits. I hope you agree with me about that evidence. And technological development now offers the best avenue for performance improvements. And in para events, particularly where the human prosthetic or machine interface is really important, we have huge potential for improvement. Okay, a little bit about riding faster. So here's an example of a svelte 90-kilogram person of my size. This is really what I wish to be, riding at 43 kilometres an hour along a flat road in what we call a touring position, basically as this rider is showing us. And so a person doing that would be generating 490 watts according to my calculations. Of that, 55% overcomes the aerodynamic drag of the cyclist himself or herself, 35% for the drag of the bike, and the rest is due to rolling resistance of the tyres. So this is essentially friction, if you like, within the tyre fabric, which generates heat, and then 2% for mechanical friction of the chain drive. If the rider, of course, lowered their body position to be much flatter, they could reduce their power requirement to 367 watts, which is, of course, what most cyclists would do. So what we learn from this, what this shows us, is that to ride faster, the primary strategy is to reduce drag. The major component of the total power output of the cyclist is going into overcoming aerodynamic drag. There are other sports where this is significant. From running, not so significant, lower speeds. Speed skating, similar speeds, similar position, similar proportion. Alpine skiing, somewhere in between, but generally very high due to high speeds. And wheelchair racing, not quite such high speeds, but still surprisingly fast. So a reasonable proportion, a significant enough proportion to be worth improving. So here are the obligatory equations. This is engineering, so you get to see the equations, at least some of them. Now, any school students here might recognise this as a free body diagram, and this is one that's got all of the forces on a cyclist plus their speed and their acceleration all shown in one picture. And we sum all of those forces together and essentially do a force balance, and then turn that into an equation which we call the equation of motion, and that's it with all of its terms. This is essentially the power, well, the P is the power of the required for the athlete to produce. This is what the athlete produces. Here is a term for the rolling resistance, the tyre resistance. Here is the aerodynamic term. Here is the gravitational term due to riding uphill or downhill. And this last one is due to acceleration. We simplify that. Mostly we don't use that entire equation, we just simplify it to the following. So the power required for the cyclist equals the speed of the cyclist over the mechanical efficiency times a term to do with rolling resistance, and we generally know what CR is, and mass of the cyclist and gravitational acceleration, so those are pretty much fixed. And then CDA, which is a term that relates to the shape of the flow, that's CD, and A is the frontal area. We'll talk about that in a moment. And then a term that relates to the density of the air and the speed of travel of the cyclist. So in the end, it's really quite simple. The most important part is CDA. We just need to minimise CDA, and we will minimise the forces on the cyclist. So the best strategy for improvement is to reduce CDA. So how do we do that? Well, the first thing is we reduce A. Now the frontal area is the silhouette area. So here is a cyclist in 4 positions, and if we just take the silhouette area, the area in black there is the frontal area. So you can actually measure it with a camera and a bit of image processing. That's generally not done in aerodynamic research because it's actually not necessary in most cases. We can also reduce the CD, the drag coefficient. That relates to the shape of the flow around the person or the object. If the flow remains attached to the body of the person and it's very smooth, generally CD is low. If it separates away and produces a large eddying mass of air behind, the CD is large. So we can control that by changing the rider position and the frontal area is changed by changing the rider position, and that's optimised with coaches. But we can also reduce the CD by changing the rider position, things like angle of the arms and the positions of the hands. And we can also optimise the bicycle design, so we're going to talk about that. And we can also optimise the clothing, the skin suits. Here are some CDA ranges. For a town bike, a person on an upright bike with a very upright body might have a CDA of about 0.65. Touring bike, that was my case with very high power requirement of 0.4. A racing position, with a much lower body like this, is about 0.3, and in a pursuit position, a little bit like the one on the right, the CDA value can go down even below 0.22, or even below 0.2. So how much power do people produce? Well, sprinters on the track produce more than 2,500 watts, even 3,000 watts I've heard reports of. Anna Mears, I read an article that said Anna Mears produces 1,800 watts. She may produce more than that for all I know, but certainly that's a very, very impressive figure. For team pursuit athletes, men produce 650 to 700 watts. My calculations of the world record last week were that the men's team pursuit produced an average of 697 watts during that race. Women, 460 to 480 watts when they're in the front position. Smaller numbers are really due to the smaller average body mass and not much else. Okay, elite sports and sports engineering. So, a significant thing happened in 1981, and that was the Australian Institute of Sport was formed, and it was formed to support elite athletes in Australia and introduce science into their support and essentially improve sport by essentially a scientific approach, and they have been extremely successful at that. Following that, Paralympic Committee was formed in 1990 with a similar task, well, certainly maybe not initially, but they have actually they're falling into a very similar role of supporting technological development and so forth in sports science. Then in 2008, the University of Adelaide started a sports engineering degree, and a number of others have followed. And that's, there's essentially been a cascade of universities moving into sports engineering, all of these universities are now working to support elite sport in Australia. And not just elite sport, all sport in Australia. Sports engineering at Adelaide, well, as I said, we commenced in 2008, and sports engineering is essentially, for us, it's a combination of mechanical engineering and biomechanics. And we also provide a lot of context, sporting context and applications during the course. So the students end up being skilled engineers and having very, very strong understanding of biomechanics, and they are excellent at applying it to the sporting context. We also formed a research group, the Biomechanics and Sports Research Group. We have 7 academics, 8 postgrad students, and we have a steady stream of honours students every year working on projects within that group. And our aims are to improve athletic performance and prevent injury. It's not just about elite sport, it's generally to improve athletic performance, and prevention of injury is really part of that. That's all of us. I won't talk about who all the people are, but we have a good range of skills within our group of academics. We have a group of fantastic postgrad students, and we also have other contributors from within our postgrad numbers, work experience students, all sorts of people who've really helped us a lot to move forward. And we have very strong collaborations. We have collaborations with the Australian Institute of Sport, Cycling Australia, South Australian Sports Institute, or SASI, and the Australian Paralympic Committee. And we all work together in various ways, and all of these organisations work with each other in various ways. It's really a big collaboration. We also collaborate with Scott Sports and Bora Hansgrohe, and we collaborate through Cycling Australia with CASC and a local engineering company, Askell. So it's all very, very fruitful. So now I would like to hand the floor over to Amy Lewis, who will talk about wheelchair sports.
Thank you. So we're going to take a little step away from cycling and look at some other athletes who are going round and round in circles as fast as they can. So we have wheelchair races, and wheelchair racing is a fairly new sport, and it was first introduced in the Olympics in 1960s. There's been major advancements to wheelchair racing, with the 1980s bringing rise to the three-wheeled wheelchair that we can see today. Athletes commonly assume a kneeling position and use a striking motion. It's important to recognise that athletes don't actually grab the wheel, they're just hitting it. These athletes can reach really high speeds, and in fact over distances of 800 metres, wheelchair racing athletes are faster than their able-bodied counterpart. There are two main schools of thought for what propulsive technique athletes should use. As Richard has already highlighted, that at high speeds, aerodynamics are quite important. So we can see the athlete on the left of the slide is using a propulsion technique which is advantageous for aerodynamics. They do stay low, however, they compromise how much time they're contacting the wheel and therefore how much force they're transferring through to the wheelchair. Alternatively, athletes can use a position which promotes powerful generation, and we can see this on the right of the screen. For this position, athletes substantially compromise their aerodynamic advantage, however are able to apply greater force over a longer push range. So an important question to understand is what aerodynamic strategies do wheelchair racing athletes employ? I did an analysis on the 2016 Rio Paralympic finalists, where I grouped each of the athletes into one of three classifications based on their trunk position. One being low, one moderate, where they start to elevate the trunk, and a high position where we see large amounts of trunk elevation. When we look at the results from these finals, we can see that for females, the athletes who are finishing in the medaling positions, so positions 1, 2 and 3, most frequently adopted low positions. However, for the males, we saw there was a more even distribution of the low and moderate positions, with these high positions being seen very infrequently. So from this we could see that for the female athletes, aerodynamic strategies were important. However, these were less important for the males in winning a race, and it's possibly due to the greater strength that the males have and are able to overcome the additional resistive forces. So if it's not for aerodynamics, how else as engineers can we improve the performance of these athletes? We first think of equipment. And although we've seen major advancements already in the equipment in the frame design of wheelchairs, we still are limited, and that's mainly to do with how unique each of these athletes are and how limited we are in using commercially available equipment to fit the unique attributes of these athletes. So a current limitation for wheelchair racing athletes is in the seating bucket. How many of you have ever tried to run a race in a pair of shoes that are 3 sizes too big? None of you? So that's what it would be like for these wheelchair racing athletes. So these athletes have either amputations or substantial muscle loss in either one or both of their legs, meaning that their seating bucket is too large for them. As a consequence, they can move relative to the seat, meaning their motions are less efficient. It is possible that because of this movement, they're not contacting the wheel optimally. And it's also possible that from this movement, they're getting blisters and lacerations from the frictional rubbing. None of these are beneficial. And so that's where we start looking at adaptive technology. This technology is the interfacing between the customised equipment needed for these athletes and the commercially available equipment. So, does customised seating interfaces, which increase conformity, lead to a better performance? We did a case study with a single athlete, and we could see substantial time differences when we included a customised seating interface, which are the red times. And so for this one athlete, we can conclusively say the conformity did increase performance substantially. Another form of equipment optimisation is in the wheelchair configuration itself. So you can change the wheelchair height, the seating angle, and many other parameters to best balance the stability and performance optimisation. Currently, athletes pick their configuration based on anecdotal knowledge and experience, so it's very perceptual and based on feel. This process is very time-consuming and expensive, as a new seat costs a few $1,000s, and so each time they want to try something new, it requires getting a new wheelchair, getting used to that wheelchair, and then deciding, no, I want a new one. So it's not common for them to be able to change, and it can take them up to 10 years to get them a good seat. We can also see from the bottom figure that within a team, there are substantial changes in impairment type and severity, and so one wheelchair doesn't suit the whole team. So how as engineers can we improve the process of rugby wheelchair design for optimal performance on an individual level? Another PhD student did some work looking at different seating parameters, including seating angle and seating height, for a number of different skill tests as seen on the web plots. When we compared the current seating configurations with an increased parameter, we can see that there were slight changes in both of these parameters. As you go further out the web, you get a greater performance factor. When we see a decrease in both of these seating parameters, however, we can see that a decreased seating angle substantially benefited all parameters of performance, whilst decreasing seating height had very little impact. So from these sorts of things, we can start to understand what each athlete needs and how we can then improve their chair to suit them perfectly. From this testing, 6 elite players decided to order new wheelchairs, and the players were all wanting to implement the changes before they were even given the results, demonstrating how beneficial this research was to them. There was also really excited coaches who commented on how much more effective and quicker using research was for these processes. To be able to identify these changes, we need to understand what the changes are. I'm sure many of you have been told in the past, practice makes perfect. But what is perfect? Without numbers, we don't know what we're trying to optimise and what we're trying to go towards. And so for those reasons, we need to start getting data. And that's so putting sensors onto a wheelchair. It's important that we can get these in field and under conditions representative of normal training and competition, so we can improve their performance under race settings. These need to be lightweight, wireless, unobtrusive to performance, and generalisable across whole teams and athlete squads. For wheelchair racing, forces need to be measured both at the seating interface as well as at the wheels. Typically, research has looked at just the interactions between the hand and the pushroom and how to get the greatest amount of force towards propulsion. However, one thing that we looked at was what the seating interfaces were actually doing towards performance. So before we look at some of the results, I just want to highlight the 2 key phases of wheelchair propulsion motion. Firstly, there's the propulsion phase, where you're in contact with the wheel and applying force to the wheelchair, as well as the recovery phase, which is between each stroke, and it's where the athlete realigns their body ready for the next stroke. If we look at the pressures acting at the seating interface between each of the 2 phases, we can see on the treadmill, there's very little change in motion, and so the athletes are sitting quite stable. So in each of these graphs, the top is in the forwards direction and you're looking downwards into the seat. We can see similar trends between track and treadmill-based steady-state propulsion, where there's still a lot of stability and not much movement at the seat. However, when we start looking at the acceleration cases, we can see that during the propulsion phase, the athletes are starting to anchor off of their leg and are using it as a mechanical advantage. We can also see this in the track starting conditions. So this is actually quite a huge finding in that the legs are able to contribute to forwards propulsion. Typically, the legs haven't been considered as a contributive factor, and so this has really been able to shape how we start training the athletes and where we can look for mechanical advantages. Instrumentation on its own can help with defining the efficiency of a motion. However, it's also important to understand the injury risks associated with a motion. So with computational modelling, we can start coupling the kinematics, so the movement patterns, with the forces that athletes are applying. And with this, we can start balancing out the performance and injury risks of motion. So we can see in the slide behind me some graphics of a simulation of a wheelchair racing propulsion, with the red elements representing the muscles. When you start looking down at a muscular level, we can look at what muscles are being recruited for a task and understand the efficiency of the motion and whether we're recruiting the largest and most effective muscles. And we can also see how much strain we're putting each of them under and whether we're likely to put them under a risk of getting a strain injury. From this sort of research too, we can start developing a normative database which can help us understand which techniques are more prone to injury risk and which techniques are more competitively advantageous. So, I did a study, and if we compare the results from two different athletes, it was quite clear that there were kinematic differences between them. We can see this through the trajectories of the hand, elbow, shoulder and head for the two athletes for 3 different speeds. Notable differences include the range of motion of their head, as well as how long their hands are in contact with the wheel, as depicted by the shaded grey regions. So what we were able to find between this case study was that the less experienced athlete had higher propulsive forces but a lower velocity, which was indicative of them having a lower efficiency motion. However, this athlete was also able to have lower joint reaction forces, and so somewhere in their kinematic patterns, they were able to reduce the stresses at the hands and have a safer motion with less risk of injury. So these computational modelling approaches are very beneficial. However, they are quite timely and it's taken me almost my whole PhD to find. So although we're able to start answering some questions, we still need to find many more. So all of the things I've presented have been a part of my PhD, and they've all led to the performance preparation of these athletes at Gold Coast. So yeah, hopefully you're all experts in wheelchair racing now, and there's some finals on tonight for the 1500 metres, which I'd strongly recommend you go home and watch. So thank you.
But don't go home yet. I would now like to introduce Sean Fitzgerald. And actually, I'll just take this little time to mention that both Sean and Amy won Best Paper Awards, 2 of the 5 Best Paper Awards at the recent International Sports Engineering Association conference in Brisbane. So, quite a fantastic result.
All right, thanks Richard. Can you hear me? Is that better? Yeah. All right. So for me, I'll be talking about some of the work we did looking more towards the Rio Games, and this is then transferred onto the Commonwealth Games at the Gold Coast. So back in 2015, me and my final year project partner, Henry Atkins, along with Richard, were given pretty much free rein over the bicycle to see how much drag we could produce to just see how much faster we could get the team to go. We had a very short timeline and a pretty limited budget, so we had to look at areas that were readily changeable and could be easily adjusted and implemented. These are mainly the seat posts, the socks, and the cranks. So I'll be going through each of these three areas. First up, we had the seat post. So on a typical off-the-shelf bicycle, the seat post will simply be a round tube. However, for all aerodynamic bicycles, all really fast bicycles, they are made from an aerofoil, which is basically a simple teardrop shape. And as you can see in this picture, it's quite large, so it can contribute significantly to the drag. So for all our aerodynamic researchers, we go through a pretty much four-step process. First up, we establish the environment, where we observe the airflow and research existing ideas. Next up, we replicate the environment in wind tunnel or on the computer through CFD, which is basically just a wind tunnel on the computer. Then once we have the environment set up, we can experiment with the design. So we set the baseline, what the current work is, we research existing ideas, and we experiment with new methods. And this is where all the fun bit happens. And once we have a final design, we need to test and validate and make sure that it works in all cases. So first up, we observe the environment. So this is a very simple experiment, but it works incredibly effectively at seeing what actually happens. So on the right, we've got wool tufts stuck on a fishing wire between the saddle and the top tube. And on the left, there's a GoPro stuck along the top tube. So this camera looks straight back at the cyclist's legs. And this is what we see. So it's not the most flattering of images, but it provides a very good indication of what the airflow is actually doing. So we can see the red wool lines go back and forth, back and forth. So the airflow remains pretty much the same magnitude and velocity, but it is highly periodic in its direction. It matches the pedal cadence, and these guys are pedaling at over 120 RPM, so it's oscillating back and forth at quite high speeds. Now the problem is, track cycling takes place inside an indoor velodrome. So the basic assumption everybody would made was they're riding around a box in still air. However, we can clearly see here the air is not still, at least for this section of the bike anyway. So all previous testing done on the seat post would have considered just straight airflow. So we can see that it's obviously different, so this will affect our results. So we replicate the environment in a wind tunnel. This is a very small wind tunnel, and it just has the seat post in it, so we've got no legs or bike, but it's really all we need. We have a small wind tunnel and we have small components so we can tune in on just that area and see what's actually happening with that one point. So here we can turn the seat post through a number of different angles. So we have straight airflow onto a turning seat post. On the track, we have a straight seat post with turning airflow. They both have two different methods to get the same result. And this is pretty much our experimental process. We start with the baseline result. We have a wool tuft, which is just a little bit of wool on the end of a stick, and that can actually see how the air is going because air is invisible and we can't see what we're doing. We can directly measure the drag force live, straight out, so we can make some changes and see what it does. And we have a lot of fun with plasticine. So it's a bit more science than giving a toddler plasticine, because we can mould the different shapes to what we want. We can experiment with the wool tuft and we can see the live drag. Once we have a bit of an idea, we can get into 3D printing. So we can create new profiles, and what we're essentially doing is creating an aerofoil, which is the exact same as what you do for aircraft wings. So I created an entire computer program that used 70-year-old equations to create aerofoil profiles to make a new seat post, and we automated this so that we could be in the tunnel one morning, decide we need to change something. Within 10 minutes, we'd have a new model. 16 hours later on the 3D printer, we'd have it ready, and be in the next day, we'd be back in the tunnel testing a new idea. So this is an incredibly fast iterative time, actually. This is faster than we would have ever been able to do it previously in wind tunnels, or even on the computer with CFD. So shown here is some of our results. So previous track cycling only considered 0 degrees, so right at the very front here, but we have to consider across the wide range of angles. So shown in blue was the current design made in carbon fibre, and you can see that is not pretty much the same across all yaw angles. However, our work dramatically decreases in drag at higher yaw angles and is a greatly lower drag. Shown in the line above is my copy. So this has the exact same profile, but is made out of different materials. So this shows the top one is the testing prototype, whereas the bottom one is the blue one is the finished product. So this shows the difference between a finished product and a prototype. So a finished product with it's done nice and smooth should always be better. So all our other results should really be dropped down by the difference between those if they were going to be made in a final product. And the final result, with a new saddle designed in collaboration with Cycling Australia and Adelaide Uni, we're able to effectively halve the drag of a seat post, which is quite a significant result. So moving on to the socks, this is an interesting little story that I quite like because lots of people ask, why do you bother? Well, at this level, every millisecond counts and our legs are remarkably inefficient and we can make a massive difference, as you will see in the end. So, but before we go into that, we need to do a bit of aerodynamic science. So we have to have a bit of science in this lecture. Basically, there is two ways of airflow around a circular cylinder, as shown here, depending on the speed of the air and the size of the object. So in the top, we have laminar airflow, where the air is nice and smooth going into the cylinder, and at about 80 degrees around the cylinder, it sort of separates and it creates this large wake. So this large wake is slow-moving air, and the larger it is, the more drag it produces. On contrast, if we have turbulent airflow, we have it separates much later, and so we have a smaller wake which reduces the drag. So in cycling, we want turbulent airflow. And how do we get that? We trip the air. So we put a little bit of obstacle along the surface, and we can add more energy to the air, increase the mixing, and reduce the size of the wake. So here is a graph of the drag of a cylinder versus the Reynolds number, which is the velocity of the object, the air, and the size of the object. We can see at low velocities it has high drag, but it reaches this significant point where it drops suddenly and the drag decreases, known as the drag crisis. So this is really good. Except for in cycling, we have, for the thigh, which is a larger object than the calf, the thigh is right on the drag crisis, so we reduce the drag significantly. So that's good. But for the calf, it's right with the high drag area. But if we add a little bit of roughness and keep adding a bit more, we can move that drag crisis to happen at a lower velocity. So we end up having the area of the calf at a low drag. So this is what we want, and this is what's used throughout different areas of cycling. For us, we worked in the socks. So we put a wire on the edge of a sock and we moved it about, put it in the exact right position, and we got significant drag reductions. But you moved it a centimetre or so, and there would be no drag reduction at all. So the position was highly important. And our solution we came up with was effectively to have multiple trips. Now you can't really see them, but in that white sock there's a number of vertical lines. So this has effectively trips everywhere. And this is the same method as they use on other areas of cycling clothing. If you watch the TV, you will see it particularly on the upper arms, but they won't use it on the thighs because it's already at the drag crisis. And this leads to patchy sort of skin suits where some areas are liney and rough and other areas will be as smooth as possible. So lastly, we did the cranksets. So the cranksets are the point where you add the pedals, you add the power to the bike. The interesting thing about them is they rotate 360 degrees, which means it's very hard to do anything aerodynamically efficient. So we had a testing set up in a wind tunnel. Once again, small wind tunnel, half a bike, but it gives us all the information we actually need to know about it. So we'd do anything, we'd find a drag reduction, say position B, and it'll be all good. We move to position C and it'll be worse than it was before. So the hard part here was trying to mould the cranksets to work at all 360 degrees. And we, once again, had fun with plasticine. So some of these ideas are quite frankly ridiculous and would never actually be implemented, but they allow us to see what's actually happening. We can mould it to the non-drive side to look like the drive side. We use the little humble wool tuft, Richard's favourite wool tuft right there, and we can see what's actually happening to the airflow. So this gives us a good idea of what's happening, why it's happening, and how we can influence it. Our final result was to look at very, very simple, but that's the whole point. We cleaned out everything. We found particularly the underside was particularly important, as we wanted to clear as much space between the cranks and the frame so the airflow had space to move around. And collating them all, we actually got a 27 watt reduction, which is ridiculously large for the amount of work we did. This is a 2-second difference over a team pursuit. However, the results don't always translate to from the wind tunnel to the track for a number of different reasons, because the wind tunnel isn't always fully representative of the track, and we're always dealing with the ideal case, which doesn't mean wind tunnels are useless. It means that it's actually what they're entirely designed for. We build a wind tunnel to focus in on one area to get the biggest reduction on that one area, and then we can then apply that in a smaller manner on the track. But this sort of leads into my PhD work, which is understanding the airflow around a cyclist in the velodrome. With this, we can translate the results from the wind tunnel to the track much more easily. We need a greater understanding of the environment inside a velodrome. And this can be used for a variety of areas, not just bike design. It can be used for athlete position and coaching styles. And so my work involves the use of measurements from inside the velodrome to build an understanding of the airflow around a cyclist, and will hopefully be used later on in the wind tunnel or in CFD to reduce the drag of the cyclist. And thank you. I'll pass on to Richard.
I'd like to introduce myself again. I'm going to talk about a couple of projects that I've been involved with and I guess led from the university's side, and which I find extremely exciting. So once I've done that, I will close by giving a bit of a summary and our way forward. So I'm about to subject you to a Richard Kelso style tirade of stuff. So I will try to move through it quickly. I have a lot of slides to cover, but I hope you find it interesting. First of all, I will talk about the Scott Cadence Plus. This is a road cycling helmet shown up in the right with Simon Gerrans, and the Casque Mistral helmet, which has been used at the current Commonwealth Games in the track cycling and the road time trial as well. So the Cadence project started in 2014, end of 2014, and proceeded through towards the end of 2016. The client is Scott Sports, a Swiss company that is a major sponsor of Mitchelton Scott, which is an Australian cycling team. Most of you will be aware of that, I hope. And my role was to do the aerodynamic design of the inside and outside of this helmet, the Cadence, which was also known while we were doing the project as the Aero 16. So I was given essentially a clean sheet of paper to do this design work. So I just went back to scratch and built up a new helmet design from essentially nothing. So the order of priorities from Scott's side of things was safety. I mean, that's a given. The whole purpose of a helmet is to provide safety for the cyclist, and safety requirements have to be met. But after that, aerodynamic performance and ventilation. Now, these were two things that in the past had been almost mutually exclusive. You could have either a very well ventilated helmet that produced a lot of drag, and an example is something like this. I'm not saying this specific helmet, but it's the old-fashioned, I call it a cheese grater style helmet. And the other end of the scale is a very low drag helmet. Let's just show this as another example of another very low drag helmet that had very little ventilation. So you could either have one or the other. So history said that you couldn't have them both at once, so we basically tried to provide both at once. Target consumer was essentially professional cyclists, as shown up there, and also for normal cyclists, the riding public, people like you and me. And also triathletes. Triathletes were the other target market. Okay, step one was to do all the patent, product and literature reviews. So I love looking at patents. You see all sorts of crazy ideas, but you also learn who's doing things and what ideas maybe you can't do without paying royalties, so you may not want to do them. The next one is to actually look at what's on the market. Those were two leading helmets at the time, and obviously we needed to improve upon them if we could, so it was very interesting to see how they worked. And the other thing is helmet literature. A little bit limited, but there was quite a lot of work on ventilation, which actually proved quite interesting and informative. As Sean said, at the start of each of these projects, you have to work out the aerodynamic environment. So we essentially did that, and in conjunction with Scott, we defined 3 positions of the head and helmet. First one is the effort position. That's the position of the head and helmet when a rider is really pushing hard. So their body will be flatter and they'll be facing a little bit more down, the head down. Relatively high speeds there, and the priority was 60%. If you want to put a weighting on all the things we were looking for, 60% of the priority was on that position. 30% was on the cruise position. That's where you're sitting in a pack of riders, heads up a little bit, generally going a little bit slower. And the other one is in the sprint. This is a Caleb Ewan kind of thing. Head down, body really flat, going hell for leather at top speed. And so less preference there, but I had my secret preference. It went 0, 0, 100 because I wanted Caleb to win, and he has. The other thing is the yaw angle range. Now, when you're riding along, there are environmental winds. So those winds create essentially they turn the airflow to the side, and so that's called the yaw angle of the flow. And so we considered on the road up to about 20 degrees of yaw angle. So we tested at those ranges of angles. Now, we had a range of speeds there, 35 to 75 kilometres an hour. And what was actually really interesting, and it's actually a fantastic result, is that with the helmet of the normal helmet size at that speed, it means that you can actually control the boundary layer, as Sean pointed out, by using roughness. And you can, like with a cylinder or a leg with a sock and so forth, you can control the drag, or at least reduce the drag on the helmet by using roughness, or, as shown here, little grooves in the surface, which effectively produce a similar result. So we have a lot of opportunity to control the flow and reduce the drag. Now, I'm an aerodynamicist, and I don't really do much heat transfer work. So I had a lot of fun generating a mathematical model which I used to essentially take my brain out of my lack of understanding out of the equation. So I developed this model of a diverging duct. Now, this diverging duct was really a model of an airflow channel through a helmet from the front of the helmet, the airflow path, and it comes out the back. And the question I asked was, is it better to have a diverging channel or a converging channel, so that the vents are, so the channel is bigger at the back or smaller at the back than it is at the front? So I set up this model on the assumption that the flow going in the front was driven by the airflow past the helmet, and the flow coming out the back was at the pressure of the back of the helmet. I looked at internal flow friction inside the duct. I assumed 32 degrees surface temperature of the head, and I generated a series of plots. Now, some of those, it's a bit hard to read what those axes mean, but what we actually see here is this is the heat transfer rate, in other words, the cooling effect, versus the height of the exit. Now, the inlet was 0.01 metres or 1 centimetre high, and so we find that when the inlet is half of that, we have low heat transfer rate, and we actually get the maximum when it's about 7.5 or 8, and then after that it drops down, but not very much. The pressure drop in the channel, that really represents the resistance to flow through. And we want the minimum resistance to flow through so we get the maximum flow. And what I found was that if you diverge the channel from 0.01 to roughly 12.5 millimetres at the back, we get actually quite a large drop in the resistance, and so we get a good flow. So around about where this red line is, you get really good heat transfer, good cooling, and you also get very little resistance to flow. So that's kind of the sweet spot. That was my determination. So if we actually just diverge those channels a little bit, we can have our cake and eat it. We can have good cooling and also low drag. Okay, so next Scott sent me a minimum thickness helmet. So this is it was actually a drawing, design of it, which we then 3D printed. 3D printing is fantastic. And we used that because with this minimum thickness helmet, we knew that we could meet certification. We knew we would have a helmet that was strong enough, so when they do their certification drop tests, it would actually produce the right protection for the rider's head. So then we got this helmet and then used that for testing, and we then added material to that. So if you add material, you make it safer, and you also have the opportunity to reduce the drag. So that's what we tried to do. And with this model, basically I used plasticine. I love plasticine. So this is actually Lars Teutenberg, who used to be at Scott. He showed us the positions they wanted. We replicated that with our wind tunnel model, our first head form, and these are the positions: cruise, effort and sprint. So as you can see, for the sprint, the head is down quite a lot. This is our very simple initial model, again using the small wind tunnel, but it's actually perfect, the perfect size for this sort of work. You can see the setup there. There's the head with the helmet on it, and it's connected to a load cell down there. That measures the drag on the head and helmet to an accuracy of 0.015%. It's pretty much the most sensitive and lowest error load cell you can buy. And we ran that at various speeds into various positions and various yaw angles in the wind tunnel. And I would investigate the flow and explore where flow separation occurred and where the flow actually travels around the surface. And I looked at different places to put trips and all sorts of things. And once I understood what that was doing, then I worked out where to start adding plasticine. And then I built out a tail that was only built out just far enough to prevent all of the bad things from happening, and added a number of other bits just to get the contour right. So the thing about this is we had live drag measurements. So you could hack a bit of plasticine or whatever off, and if it made things worse, you could just put it straight back on again. So there were no penalties for making a mistake, and it allowed the flow to actually teach you what was happening. And of course, the thing is, you had to try and understand why the changes actually had an effect. So it wasn't a random process, but it was live, and we could also record the results for later processing. We did air velocity measurements using velocity probes around the helmet to work out where it was fastest and slowest, used plasticine and protrusions and so forth. That's some of our live feed up. Now, preliminary results, that's the cadence. That's at least this model up here versus a reference model. Quite a significant improvement. That's not non-zero axis there, but it is a significant improvement. We're looking at 12 to 20% less drag than the reference, which was pretty good. So, but our helmet didn't have all the straps and didn't have vents and so forth. So the next step was to take that shape and actually build it onto an existing helmet. So I basically filled in an existing helmet and plasticined it up and produced this. I played with With vents, I varied their size and put them in different sizes, put them in different places, and try and optimise it all for the various flow angles and so forth. I formed the internal flow angles and maximised the ventilation flow, and also found that as you maximise the internal flow, you reduce the drag. So the vents actually produce very little drag. And we also found that no top vents are required. The best approach is, in fact, we found just simply have the air going in the front and out the back. All the vents in the middle don't actually help very much at all. But one of the really good things about this is it was a working helmet, so I could put it on my head and I would ride home with it and then back to work each day. People just thought I was a bit mad, but wearing a plasticine helmet. But it was actually really informative because I learned how well the helmet worked as a real product. Then Ryan Leckness, who was one of our PhD students at the time, now finished, turned that into a CAD model, computer-aided design model. He's brilliant with CAD, and he transferred that into a fantastic shape, which then was sent over to Switzerland, where their industrial designers and safety structural designers started working with it. There was a lot of interplay between us. We had a lot of discussions where we talked about trip designs and getting clearances and all this sort of stuff so that we could maintain all of the optimum design for best performance, aerodynamic and ventilation performance. And so it was a kind of a discussion. Sometimes it was a bit of a competition between aesthetic design and aerodynamic requirements, but I think in the end we all won. And it produced a fantastic design, and that's their version of it. Then, once they had pre-production samples, we launched into a testing campaign, and Sean and Henry were involved in that. Sean, who spoke before, and Henry, his partner from his final year project. We developed a heated head form, so that's actually shown here. It's a head with a 30-watt heater inside and temperature sensors all over. And so we run that up to temperature and put a helmet on, test it, have it with the airflow running in the wind tunnel. 50 minutes later, everything's reached an equilibrium. We measure all of the temperatures using thermocouple loggers all over the surface. And then we also grab thermal images. So we can do a lot of diagnosis about where there are hot spots and cool spots on the helmet, and we can understand a lot about the airflow. So we also developed a small blower wind tunnel for use just here at North Terrace, so we could test at any time and do it essentially in secret. And so we did the testing on this model. So here is the result for the effort condition. Now, what I haven't mentioned so far is that there was a version of this Cadence helmet, the final Cajun helmet, and that is with plugs. So here are the results for the drag. Now, the drag is, in engineering, we would normally measure that in newtons or Newton. But in cycling, people tend to talk in grams, and so I think most people have a bit more of an understanding of grams, so I've left it as grams. So here's the drag in grams of the head and helmet, not just... So when you put a helmet on, you're still measuring the drag of the head and the face and so forth. So there's the bare head. There's the Cadence with plugs. This is the final Cadence helmet, but with plugs filling in the vents. And this is the lowest drag helmet that we tested, and it's barely any more than the bare head. This was one of the competitor helmets, which incidentally has very low drag, but the cooling isn't nearly as good as the Cadence without the plugs. So in the Cadence we sacrifice a tiny bit, at least just in this condition, a tiny bit in the effort condition in terms of drag, but we gain a whole lot in ventilation, and that helps the rider to perform. Here are a whole lot of other competitor helmets. The Vanish Aero, that's this helmet here. I actually helped to develop that, and that was the previous aerodynamic helmet. So we replaced the Vanish Aero with the Cadence helmet here. So a significant improvement. The Centric I haven't mentioned, but that's a kind of a sister helmet to the Cadence. It was developed at the same time, and its design was informed by the Cadence development, although we didn't actually do any testing along the way. So that's the Centric there, and the original helmet that we started with was the Vanish Evo, which is what I described as the cheese grater style. I don't mean that in a derogatory sense, it's that kind of open structure helmet. So you can see that we've gone from about 300 grams in the original helmet, and we're around 110, 115 grams for the drag on the helmet and head in each of these cases, a significant improvement. Here are some of the thermal results, and so there are a whole lot of different helmets that we tested. BH's bare head and the Cadence is shown here in its two configurations, and we find that we actually have quantitative measurements of those from all the temperature sensors, and we show that the helmet is extremely effective in the cooling sense. Okay, the result of this development process is now we have 3 helmets in one, from one development process. We have the Cadence with the plugs, shown here, conveniently all in one picture. This is what was the Orica Scott cycling team, now Mitchelton Scott, but yeah, Cadence with plugs, Damien Howson, and that has the lowest drag of any of the helmets that we tested. The Cadence without the plugs, so a lot more ventilation, a little bit more drag, and it is the coolest of the MIPS equipped, means it's got an extra safety feature in it. The coolest of those helmets available, and it's actually now the triathlete's preference helmet. The British triathlon team seem to have adopted it as their helmet for the Commonwealth Games. The Centric is this one here following behind, and that's as well cooled as any other helmet we tested. It's an amazing helmet. So one result is, yes, it's possible to have low drag and excellent cooling. Performance impact. So when you assess performance impact, it's really a good idea just to take a double scenario. You say, all right, you've got 2 cyclists who are identical. One is wearing one helmet, the other is wearing the other helmet. They produce the same amount of power and they target the same speed. So, and their bodies are in the same position. Everything else is the same. So speed is actually dictated by their power output. So we assumed a 70 kilogram rider, 650 watts produced, basically in a seated sprint. If they were wearing the Scott Vanish Evo, the old standard helmet used by Scott, a premium helmet that was used by the team, the speed would be about 58 kilometres an hour, and they would cover 200 metres in 12.42 metres seconds. Wearing the Scott Cadence Plus with plugs, we get a speed increase of 1.1 kilometres an hour and a reduction of 0.43 seconds and 3.8 metres margin. So 2 identical people sprinting to the line with 2 helmets, 3.8 metres separates them. It's a huge improvement. Okay, so this is now the Cask Mistral project, which went from 2015 to 16, just before the Rio Olympics. It was funded by an innovation grant from the Australian Institute of Sport, and it was essentially a collaboration with Cycling Australia. My role was as an aerodynamic designer, and it was really a team effort between me and Andy Waugh and various other people at Cycling Australia. Okay, the test system was the mannequin that we discussed before. So the mannequin is shown here. The head can be put in different positions, both up and down and different tilt angles, and so we can set it up to match the positions of athletes. And we can measure the drag or the forces on the head and helmet from a load cell in the neck and also one in the base of the equipment, so that we can actually measure the drag on the whole, and particularly the changes from going from one helmet to another. very high accuracy force measurements again, and we matched the positions of the mannequin and the head to the positions in the low position standard and high positions for the men and women in the then Olympic team. And we set the wind tunnel speed to 16 metres a second, which was pretty much halfway between the men and the women, so it covered really both of those scenarios. We tested a whole bunch of different contemporary helmets, from fantastic ones to a really cheap model, which is actually not too bad, and used that as a benchmarking process. So the development really was, it was an accelerated development. We had to do it very, very quickly, and we actually found that we decided the best approach was to use a casque bambino. Now this helmet is actually, it's a brilliant helmet in its own right. It's a stumpy-tailed time trial helmet, but one of these days almost unique features of it is it's actually made as a foam liner with an external shell, and they're just glued together for the final product. What it actually meant was we could take a standard shell, which provides all of the safety and is essentially the part that's certified for safety, plus all of the pads and straps and all of that kind of hardware, and we can just put a new shell on the helmet. So it takes a huge cost and time out of the whole process. And that was a decision that was made by both Cycling Australia and us, and it was something that actually made a huge difference in the project. So one of the things about the foam liner was also it was very thin, so it meant that we could develop a helmet with a minimum size, and as you saw, if you minimise the frontal area, you also minimise the drag. So the process was to replace the outer shell of the helmet, and another thing was that this whole point of using an existing helmet as the base meant it reduced the risk of the whole process. Okay, wind tunnel tests were performed in January and February, and I'll cut out all the detail, but we modified the Bambino with a new outer shell, used a lot of plasticine, tried all sorts of new design concepts, with many iterations. And this is what we ended up with. Competitor A, that was really our reference. There are other couple of competitors that were extremely good. The Mistral, the prototype that we had, shown here with lots of plasticine on the back and elsewhere, lots of vinyl tape as well, produced a saving of 4.7 watts. Ultimately, the prototype that we got back from CASC at the end did slightly better than that due to a smoother surface, better surface finishes, 5.72 watts. So the resulting design had lower drag in all the different head positions for male and female athletes, and it was also much less sensitive to position. When athletes get tired, they tend to drop their head, or they might turn their head or even lift their head. And with most helmets, particularly long tail ones, that might put a big bit of tail into the air to produce drag. This is a very short helmet, and it's very insensitive to its position. So that's actually an advantage. So if an athlete gets tired, it's not a great cost aerodynamically. So prototyping was done by a fantastic company in Adelaide called Askill, and they produced a 3D printed shell that went onto a standard CASC inner, and then we had a helmet to test. It was sent to Scott, and it came back as a pre-production prototype in June, which we then tested at 5.7 and 5.72 watts saving over the previous, or over our reference. It became known as a CASC Mistral, and it was used by the Australian Olympic team, and now it's available for sale worldwide. So it's used by our Commonwealth Games athletes, but it's also used by other teams. It was used by Team New Zealand, or the New Zealand cycling team in the track. What's the impact? Well, I did the same calculations as before. and extrapolating from that particular speed to the actual speeds for the men and women at their world record paces, the impact of this helmet on the women's team pursuit is a speed increase of not much, 0.064, but over 4,000 metres, that's a time reduction of a second and a gain of 16 metres, quite substantial. And in the men's team pursuit, because of the higher speeds and various other things, then a smaller speed increase, but again, a significant time reduction and a fantastic speed gain. Now, what's the significance of this 0.57 to 1? Well, the winning margin at Rio was 0.76 for the men. Now, in the men, they broke the previous world record in that event. It's just the British team were slightly faster, but their margin was 0.76 seconds. So what a difference a helmet can make. Just one particular component in their equipment. So they're into the tirade, and I want to reintroduce myself for the closing comments. So in the 2018 Commonwealth Games, quite a lot of equipment was actually developed jointly with the University of Adelaide. There's the Casque Mistral helmet, and that was used by the track team sprint, the track time trial, track pursuit, and blind and visually impaired events, the paracycling events. And as some people might have noted today, it's also been used in the road time trial event, and Cam Meyer, in fact, won that. And Callum Scottson came fourth in spite of having a puncture, so he did remarkably well too. The Scott Cadence we don't know quite yet, but will quite possibly be used by up to half of the road cycling team because of their normal sponsorship, or their normal professional teams. They tend to use the same helmets as they use in their professional teams. We don't know that for sure, but I think it's quite likely. And we do know that the triathlon athletes for the British team have been using them. The track bikes, the track events are all over now, but they did extraordinarily well. The track bike and its various components and the socks have also benefited from our work. A little bit of context. Okay, some notable results. Well, for a start, I just want to mention medals. So here are the medals, bronze, silver and gold, as a proportion of total medals on offer. So for various years of Commonwealth Games from 2002. So Australia achieved something like 24% of the gold medals available at the 2018 Commonwealth Games, which is a fantastic effort. Slight upturn there, probably at the expense of silver, which has dropped. So there's been a conversion of silver into gold, it would appear. But really, all of these results are wavering with a range, and they all look pretty consistent. Okay, women's 4,000 metre team pursuit. They achieved gold and a Commonwealth Games record, as did the men's 1,000 metre time trial. So these are fantastic results. But the one that is absolutely a measurable performance against other benchmarks is a world record, and that was achieved by the men's 4,000 metres team pursuit. So they surpassed the previous record quite considerably. So their time of 3 minutes 49.804 was first sub 350 time. And if you want to compare it with their previous equipment setup, we can compare with the 2012 Olympic time, because our bits and pieces were included in 2016. So we've had a 2% improvement since 2012 and a 0.5% improvement since 2016. And so it's a steady performance improvement. So, technical improvement contribution. Now, Sean mentioned the power savings from what he described, and I've mentioned my power savings, they all add up to about 33 watts. But in cycling, what you actually get is interaction between the components actually reduces that. So Cycling Australia say that they calculate around about a 16 watt improvement or advantage was generated by all of that. That's equivalent to a time saving about 0.8%. But there's been a 2% improvement. So where does that come from? Well, it comes from position changes. The positions of the athletes, their arms and their overall body position, that has been improved. There's also training, preparation, tactics and motivation. There are all sorts of factors that we can't even account for that cause this kind of fantastic performance improvement. Okay, so what we've learned is that in sports, 2 plus 2 is not 4. We were expecting 33 watts improvement, we got 16. And that's not just in aerodynamics, that's in all areas. So we've maybe found that 2 plus 2 is more like 2.5 or maybe 2. It's just not simple. And that's due to interactions between the athletes and components and between the components and themselves, and particularly in the para-sports due to the unique attributes of the athletes and how they fit to their equipment. We have to apply a systems approach in our work in the future. The athlete equipment system is very, very complex and has lots of interacting parts. It is a system. So in aerodynamics, we have to understand the flow around the bicycle rider, and the limiting thing is we don't get enough wind tunnel time at full scale. The athletes don't spend enough time in the wind tunnel. So this is one of the reasons why the state government is now supporting the development of a wind tunnel built right next to the Adelaide Superdrome. In fact, under the same roof. And what that will mean, this is a full industrial scale wind tunnel built right on the side of the velodrome. It will allow aerodynamics optimization to be part of the daily training regime of the cyclists. They'll be able to ride from the track into the wind tunnel, establish new positions, test new equipment, and then go out onto the track and actually see whether it worked in reality. And there'll be a lot more understanding that comes from that. There'll be accelerated development of a technology, which is obviously where we come in, and the fantastic thing is it's not just cycling, it will be all aerodynamic sports. It'll be all para-sports, it'll be every sport that has anything to do with aerodynamics. They will all benefit from this. It'll be a national facility. It will also be available to local industry, particularly cycling industry, so that will help South Australia. And written in the bottom line is university collaboration. So they're expecting South Australian universities and indeed other universities around Australia to collaborate in this project. There'll also be a national BMX facility and a refurbishment, and it's all funded by the state government and the federal government through the AIS. What are we doing in Adelaide? Well, we already have our own big wind tunnel that's also used in other areas of research. We have some time that we can devote to cycling. And so we've been for some years developing testing facilities for there. And this is one of the facilities that was developed, in fact, by some final year students last year. It is absolutely spectacular how well it works. And so we can test athletes within our wind tunnel, and there's a hand cyclist who was working with us a few years ago, and we're about to start 3D printing models of athletes so that we can do not just a fiberglass mannequin, but actually a real person mannequin, if you like, in our wind tunnel. I keep clicking to the right. Here we are. So, acknowledgements. Big acknowledgement to the Australian Institute of Sport and Cycling Australia, and in particular Andy Waugh. He's up there somewhere, but he has breathed life into everything that we're doing. He's been just fantastic, and so we can't thank him enough for what he's done to support us, and I hope that we have returned the favour. South Australian Sports Institute, the Australian Paralympic Committee have all had a large contribution to what we do. Scott Sports and Bora Hansgrohe in particular have been fantastic with other aspects of our work. The faculty has been extremely supportive and basically helped us along. The School of Mechanical Engineering, they allowed me to build a really noisy wind tunnel above the school's meeting room. I mean, so, you know, even just for that, that's a fantastic thing. And the ECMS and previously mechanical engineering workshops, we build a lot of our equipment ourselves, bespoke, if you like, testing equipment. And we do some of it with our own hands, and we go down there and we work in the workshop alongside the technicians. And they provide a lot of help, and they also do brilliant work in building our equipment for us. So we can't thank them enough either. I will stop talking now. So thank you very much.
Well, I am aware of the time, and I'm also aware that people have other commitments, so we'll close there. We won't actually have questions, but the speakers have agreed to stay back, and so those of you who do have questions, please just walk down to the front and engage the speakers and ask those questions. They've done some fantastic work, as you can see, and it does always amaze me what you can achieve with supercomputers, 3D printers, plasticine and red wool. And I now understand that diversity of purchase orders much better than I did previously, Richard. I do want to thank the audience for being here today and just point out that our next Research Tuesday will be on the 8th of May. It's entitled First Ferment. Our next event will actually be held a couple of weeks before Reconciliation Week, and so we'll be delving into ancient fermentation practices used by Indigenous Australians. We hope to see you all there. If you wish to stay back and ask some questions, please do. Otherwise, thank you all again for coming tonight, and good night.